Have you ever asked questions about the universe only to find yourself faced with even deeper and more mysterious questions? What was there before the beginning of the universe? How does the universe create something from nothing? If the universe formed from nothing, who created the nothing? Why can't we see 95% of the universe? How many galaxies are in the universe? If the universe is expanding, where is the center? What shape is the universe? How do we know the age of the universe? Is the entire universe the same age? Is time travel possible in our universe? How do we study the universe as a whole? How early life have appeared in the universe? Are we alone in the universe? Was the entire universe made just for us? How much of the universe can humanity ever see? Where is the edge of the universe? What exists outside the edge of the universe? Does the universe have higher dimensions? If multiple universes exist, can we travel from one universe to another? What is the ultimate fate of the universe? Let's delve into the answers to these questions with a comprehensive scientific perspective. Thanks to Brilliant for sponsoring this video. The Big Bang Theory posits that the universe originated from an extraordinarily dense and hot point, known as a singularity. To elaborate, a singularity is a unique point in the fabric of space-time where the density of both energy and mass soar to infinite levels, effectively making all spatial dimensions collapse to an infinitesimal point. In layman's terms, this means that at the singularity, our usual understanding of space, time, and matter becomes irrelevant or breaks down completely. The existence of such a singularity has led to a plethora of fascinating and complex questions. For instance, if the singularity is a state where standard physics doesn't apply, what are the rules governing its existence? What is the origin or cause of this singularity? And what set of circumstances or pre-existing conditions could have led to the explosive event we refer to as the Big Bang? Building on the foundations of classical physics, Albert Einstein's theory of relativity fundamentally transformed our perception of the universe by offering a groundbreaking framework that intricately links mass and time. According to his revolutionary theory, the flow of time is not a fixed constant, but is actually relative, varying based on the gravitational fields produced by objects with significant mass. To elaborate, Einstein demonstrated that Earth's considerable mass exerts a strong gravitational pull that distorts the surrounding space-time fabric. This distortion leads to a subtle slowing down of time for someone situated on Earth's surface, as opposed to an astronaut experiencing the weaker gravitational field in outer space. While the difference in time dilation between these two settings is minuscule, so much so that it's almost imperceptible in everyday life, it has been confirmed through scientific experiments and stands as a verifiable, real-world phenomenon. American scientists Robert Pound and Glenn Rebke confirmed through experiments that a clock on Earth runs slower than 1 elevated 22.5 meters, aligning with relativity's predictions. Essentially, mass slows down time, and the pre-Big Bang singularity, containing all mass, would stop time. Einstein thus argued that before the Big Bang is a meaningless concept. However, Einstein's idea that nothing preceded the singularity is unsettling as it negates the concept of a past. Despite this, the scientific community largely backs the Big Bang theory, supported by evidence like the universe's expansion and the cosmic microwave background radiation. This cosmic microwave background radiation, which serves as a crucial piece of evidence supporting the Big Bang theory, originated during a specific period known as the era of hydrogen recombination. This era occurred approximately 379,000 years after the initial Big Bang event. According to the prevailing Big Bang model, the universe initially existed in an incredibly small, atom-sized state. From that minuscule beginning, it has evolved through a series of well-defined phases or epochs, each with its own distinct characteristics. These epochs are known as the Planck epoch, the Grand Unification epoch, the Inflationary epoch, the Electroweak epoch, the Quark epoch, and finally, the Hadron epoch. Throughout these epochs, various fundamental particles and forces underwent transformations to arrive at their current states. When considering the universe at such an immense scale, the laws of quantum mechanics begin to take precedence over classical physics. This shift in the applicable physical laws led renowned cosmologists like Stephen Hawking to ponder the implications of applying quantum theory to the entire universe, not just to subatomic particles. This line of inquiry led to the development of a new field known as inflationary quantum cosmology. Quantum cosmology offers an alternative view on the issue of the singularity and the notion that nothing existed before it. Unlike classical theories that define the singularity as a point with zero volume, quantum theory introduces an element of uncertainty, making it impossible to specify the exact moment the universe was created. This uncertainty in quantum mechanics also allows for particles to spontaneously appear from what is termed a vacuum, leading to the hypothesis that the universe itself could have originated from a quantum fluctuation. However, it's worth noting that in physics, a vacuum is not a state of absolute emptiness, but rather a state devoid of particles. Heisenberg's uncertainty principle, a cornerstone in the field of quantum mechanics, posits that there are inherent limitations when it comes to the simultaneous measurement of certain pairs of properties of a particle. To put it more explicitly, the principle states that the more precisely one can determine a particle's position, the less precisely one can know its momentum, and vice versa. This principle introduces a fundamental fuzziness into the very fabric of reality at the quantum level. In classical physics, one might imagine that a perfect vacuum would be a state where all field values are consistently zero. However, the Heisenberg uncertainty principle throws a wrench into this idea. According to the principle, if you know the value of a field with absolute certainty, then the rate at which that field changes becomes entirely unpredictable or random. This essentially means that the field value cannot remain at zero at all times. As a result, the classical concept of a stable, unchanging vacuum is fundamentally at odds with the principles of quantum mechanics, leading to the conclusion that the notion of absolute emptiness is a theoretical impossibility. The idea that a universe teeming with hundreds of billions of galaxies could spontaneously emerge from a state of nothingness seems counterintuitive, to say the least. However, Einstein's iconic equation, E equals mc squared, provides some insights into this paradox. According to this equation, the enormous amount of positive energy stored in stars, galaxies, and other celestial bodies must be counterbalanced by an equivalent amount of negative energy, which manifests as gravitational attraction. In a universe that is closed, or one that will eventually collapse back onto itself, these positive and negative energies would have to perfectly cancel each other out, resulting in a net energy of zero for the universe as a whole. Stephen Hawking questioned how a universe with zero total energy could arise from nothing, given that creating matter requires positive energy. He noted that gravity, which has negative energy, could balance this out. However, before a star's negative gravitational energy can surpass its matter's positive energy, it collapses into a black hole with positive energy, making empty space stable. Quantum mechanics supports this view. American physicist Alexander Vilenkin showed that a small energy-filled vacuum can spontaneously appear from nothing and, driven by cosmic inflation's negative pressure, expand into a Big Bang, creating a universe from a sustainable state of nothingness where time is irrelevant. The quest to understand the universe inevitably leads to a series of ever-expanding questions about its origins and fundamental nature. Regardless of the specific subject of inquiry, the ultimate questions about the universe's inception and the emergence of something from nothing remain constant. Despite advances in science, these foundational questions persist. How did the initial conditions for everything we know come into existence? The ultimate question boils down to understanding how something could have originated from a state of nothingness. In scientific terms, the question of how the universe or the Big Bang emerged from a state of nothing remains one of the most profound and challenging questions. The inquiry not only seeks to understand the origins of all that exists, but also aims to comprehend the initial conditions that led to the universe's formation. Although scientific research has made significant strides, these fundamental questions about the universe's origins continue to elude complete understanding. Today's observations of the universe, accounting for known uncertainties, present a remarkably coherent picture. The universe consists of matter as opposed to antimatter, follows uniform physical laws across space and time, and originated from a hot Big Bang approximately 13.8 billion years ago. Governed by the principles of general relativity, the universe is in a state of expansion, cooling, and gravitational interaction. It is primarily composed of dark energy, making up 68%, and dark matter, accounting for 27%. with the remaining components being ordinary matter, neutrinos, and radiation. Presently, the universe is populated with galaxies, stars, planets, heavy elements, and at least in one location, life forms with intelligence and technological capabilities. These complex structures did not always exist, but emerged through cosmic evolution. Scientists in the 20th century made significant strides in outlining the timeline that explains how the universe transitioned from a homogeneous state, made solely of hydrogen and helium, to the complex, structure-rich universe we observe today. Starting from the present, we can trace back in time to inquire about the origins of each specific structure or component. For every answer obtained, the subsequent question becomes, where did that originate and how did it come into being? Until we reach a point where the only response is, we don't know, at least not yet. Finally, we can ponder what we do know and question, how did this come into existence? And is it possible that it emerged from nothing? Let's begin the exploration. The existence of life today is a result of complex molecules, which must have evolved from the atoms found in the periodic table. These atoms constitute the basic building blocks of all the ordinary matter in the universe as we know it. The universe did not come into existence with these atoms pre-formed. Rather, they were synthesized through multiple cycles of stellar birth and death. The byproducts of these nuclear reactions were then incorporated into subsequent generations of stars. Without this process, the formation of planets and complex chemistry would not be feasible. To form the stars and galaxies we observe today, several conditions must be met. Gravitational forces are needed to merge smaller galaxies and star clusters, thereby creating larger galaxies and initiating new cycles of star formation. This process requires the existence of pre-existing mass accumulations, which are formed through gravitational growth. These accumulations, in turn, necessitate the early formation of dark matter halos to prevent the newly formed stars from ejecting matter back into the intergalactic medium. An appropriate balance of ordinary matter, dark matter, and radiation is also needed to produce phenomena like the cosmic microwave background and the light elements that were synthesized in the hot Big Bang. Initial density variations, or seed fluctuations, are required for these structures to grow gravitationally. Finally, mechanisms must exist for generating these density variations, as well as for creating dark matter and the initial amounts of ordinary matter. These conditions are critical in the early stages of the hot Big Bang to result in the universe as we know it today. Assuming that the laws of physics, space-time, and matter-energy also need to exist, these should be considered essential elements that must somehow come into existence. In summary, when considering whether a universe can originate from nothing, these are the yet-to-be-explained, novel factors that must somehow be generated. To understand why there is more matter than antimatter, it's necessary to look back to the early universe, a period when our understanding of physics is notably uncertain. The current laws of physics exhibit a kind of symmetry between matter and antimatter, meaning that every known reaction either creates or destroys matter and antimatter in equal quantities. However, the early universe, despite its hot and dense conditions conducive to the abundant creation of both matter and antimatter, must have had a mechanism to establish a matter-antimatter imbalance where none initially existed. Various methods could achieve this imbalance. While the exact mechanism in our young universe remains unknown, any viable approach would involve three key components: a set of conditions that are out of equilibrium, naturally occurring in an expanding and cooling universe; a means to facilitate interactions that violate baryon number, which the standard model permits through Sphaleron interactions; and a mechanism to produce sufficient C and CP violation to establish a significant matter-antimatter asymmetry. The standard model contains all these elements, albeit insufficiently. If one views a universe with a matter-antimatter symmetry as a universe from nothing, then it's highly likely that the universe did indeed generate something from nothing, although the precise mechanism remains uncertain. Similarly, there are several credible mechanisms for the formation of dark matter. Comprehensive testing and exploration have confirmed that dark matter cannot be composed of any particles that exist within the standard model. Its actual essence calls for an extension of physics beyond our current knowledge. Among the potential methods for its formation are its thermal generation in the early, hot universe, which didn't fully annihilate and left behind stable particles such as the lightest supersymmetric or Kaluza-Klein particles. Another possibility is its emergence from a spontaneous phase transition as the universe expanded and cooled, extracting massive particles like axions from the quantum vacuum. It could also be a new form of neutrino that either blends with known neutrinos, referred to as a sterile neutrino, or exists as a heavy right-handed neutrino alongside conventional neutrinos. Alternatively, it could have originated as a purely gravitational phenomenon, resulting in the formation of an ultramassive particle like a wimpzilla. The existence of dark matter in today's universe leads to the question of its necessity, especially when the early universe seemed to function well without it. A mechanism must have been in place to create this substance where it previously did not exist, and each of these scenarios requires energy. This naturally leads to the subsequent question: what is the origin of the energy needed for these processes? According to the theory of cosmic inflation, which is the leading hypothesis for the origins of the universe prior to the Big Bang, the universe may have indeed originated from nothing. This concept requires some elaboration and is often what is meant by the phrase, a universe from nothing. When contemplating the initial phases of the hot Big Bang, one must consider conditions that were extremely hot, dense, high energy, and nearly uniform. When the question arises, how did this come to be? There are generally two avenues for explanation. One could assert that the universe was simply born this way. According to this perspective, the universe came into existence with these properties, referred to as initial conditions, and no further explanation is required. In theoretical physics, this approach is described as abandoning the quest for explanation. Alternatively, one could follow the typical approach of theoretical physicists, to devise a theoretical framework that could account for these initial conditions. This involves making specific predictions that diverge from those of the prevailing standard theory, followed by efforts to measure these critical parameters. The theory of cosmic inflation emerged from this second approach, fundamentally altering our understanding of how the universe came into existence. Rather than tracing hot and dense conditions back to an infinitely hot, infinitely dense singularity, the theory of inflation proposes that the hot Big Bang was preceded by a phase in which an exceedingly high energy density existed within the very fabric of space. This caused the universe to expand at an accelerating or inflationary rate. When this inflationary period concluded, the energy was converted into matter, antimatter, and radiation, resulting in what is observed as the hot Big Bang, essentially the aftermath of inflation. In more technical terms, this not only yields a universe with a uniform temperature, spatial flatness, and an absence of residual artifacts from a theoretical grand unified era, but also forecasts a specific kind and range of seed, density, fluctuations. These predictions were subsequently confirmed through observation. Thus, starting from what is essentially empty space, albeit space filled with a significant amount of field energy, a natural process has given rise to the entire observable universe, replete with complex structures, as it is seen today. This concept of a universe emerging from nothing is the central tenet of the inflationary theory, although it doesn't satisfy everyone's quest for understanding. For a significant number of people, the idea of a universe where space-time, the laws of physics, fundamental constants, and some level of non-zero field energy still exist in the fabric of space is far removed from the concept of true nothingness. After all, it's possible to imagine a location that exists outside of space, a moment that is beyond the limits of time, and conditions that are not bound by any physical laws. These ideas, if seen as prerequisites for achieving a state of true nothingness, are philosophically valid. This underscores the difference between the philosophical concept of nothingness and its more physically based definition. There are 4 scientific ways to define nothing, each context-dependent. These include a moment when the subject of interest did not exist, a condition of empty physical space, a state of empty space-time at its lowest energy level, and whatever remains after the entire universe and its governing laws are removed. If one uses the first 2 definitions, it's plausible to say that a universe could come from nothing. However, using the 3rd definition makes this impossible, and with the 4th, due to a lack of sufficient knowledge, it's uncertain what the outcome would be. Without a physical theory to describe what exists beyond the universe and outside the existing physical laws, the concept of true nothingness remains undefined in physical terms. In the realm of physics, the concept of absolute nothingness is inherently problematic. What does it signify to exist beyond space and time? And how could space and time logically and predictably originate from a state of non-being? How can the emergence of space-time be pinpointed to a specific location or moment when the very definitions of location and time depend on its existence? From where do the governing principles of quanta, encompassing both fields and particles, originate? This line of reasoning even presupposes that space, time, and the physical laws were not eternal, although they might well be. Any counter-arguments or proofs depend on assumptions that have not been conclusively validated under the conditions to which they would be applied. If one adopts a physical interpretation of nothing, then it does appear that the universe as currently understood emerged from nothing. However, if one steps outside the bounds of physical limitations, certainty about our ultimate cosmic origins vanishes. Regrettably, the nature of cosmic inflation inherently eliminates any information that could be derived from a pre-existing state in our observable universe. Despite the boundless scope of human imagination, conclusions can only be drawn about subjects that can be tested within the framework of our physical reality. Regardless of the logical coherence of any other ideas, including the concept of absolute nothingness, they remain mental constructs. The cosmos, as we observe it now, is undoubtedly filled with matter. Everything we touch, see, and engage with is composed of minute particles at its core, and over the course of cosmic history, these particles have formed into vast structures like humans, celestial bodies, stars, galaxies, and clusters of galaxies. They all adhere to the same physical laws and are part of the same space-time continuum. Everything we witness and encounter in the cosmos has existed for only a limited period. There was a time when the universe lacked galaxies, stars, or even atoms, indicating they emerged at some juncture. But where did they originate? While it might seem intuitive to say from something, it's possible they came from nothing. In this context, how does a scientist define nothing? From a scientific viewpoint, there are 4 distinct interpretations to consider. The initial concept of nothing for scientists refers to a state where the essential components to produce your something were absent. Galaxies, stars, planets, and humans cannot exist without the necessary particles to construct them. Everything we are familiar with and engage with consists of subatomic material particles. These are the foundational elements that shape our universe as we perceive it. If we begin with a universe abundant in matter, we grasp how it can grow, cool down, and be influenced by gravity to evolve into the universe we recognize today. We comprehend the life cycle of stars, which results in the formation of heavier elements that pave the way for the birth of smaller stars, terrestrial planets, organic compounds, and ultimately, the potential for life. But the question arises, how did we end up with a universe dominated by matter and not one with balanced quantities of matter and antimatter? This represents the primary scientific interpretation of deriving something from nothing. It's a profound conundrum in physics. If the principles of physics dictate that matter and antimatter can only be produced in identical quantities, how did our universe evolve to be composed entirely of matter, with no trace of antimatter? Every celestial body, star, and galaxy we've observed is confirmed to be constituted of matter, not antimatter. So how did we manage to have a surplus of these vital foundational elements if the universe didn't start with such a surplus? This is the essence of the statement that the matter in our universe emerged from nothingness. The mystery of why there's more matter than antimatter, a challenge referred to as baryogenesis within the physics realm, stands as one of the most perplexing unsolved questions in contemporary physics. Numerous theories and processes have been suggested, and while they seem theoretically feasible, the definitive answer remains elusive. We're still uncertain why there's an imbalance, more matter than antimatter, instead of a perfect balance, equal proportions, in the first place. The second interpretation of nothing for scientists is the emptiness of vast space. Maybe you lean towards a definition of nothing that genuinely encompasses no things whatsoever. If that's your perspective, then the first explanation falls short, since it undeniably contains something. To truly grasp the concept of nothingness, every basic element of matter must be eradicated. Every single radiation quantum must vanish. Every particle and antiparticle, from the elusive neutrino to the mysterious substance of dark matter, has to be eliminated. If you could manage to expel them all, without exception, what would remain is just the vast expanse of empty space, devoid of particles or antiparticles, absent of matter or radiation, and lacking any discernible quanta in your universe. You'd be left with the sheer emptiness of space. For some, this epitomizes the genuine scientific meaning of nothingness. Yet, even in this highly constrained and imaginative setting, certain fundamental aspects persist. The foundational laws of physics remain intact, implying that quantum fields continue to pervade the universe. This encompasses the electromagnetic field, the gravitational field, the Higgs field, and fields associated with nuclear forces. Space-time remains, dictated by the principles of general relativity. All the essential constants are still present, retaining the values we've observed. And perhaps most crucially, the inherent energy of space, known as the zero-point energy, persists and maintains its current positive, non-zero magnitude. In the present day, this is evident as dark energy. Prior to the Big Bang, it was manifested as cosmic inflation, which culminated in the birth of the entire universe. This gives rise to the notion of a universe from nothing. Even in the absence of any form of matter or radiation, this version of nothing still results in a captivating universe. The third interpretation of nothing for scientists is the conceptualization of nothingness as the ultimate lowest energy state achievable for spacetime. Presently, our universe possesses a zero-point energy, a form of energy intrinsic to space, which holds a positive, non-zero value. We're uncertain if this represents the genuine base state of the universe, meaning the absolute minimum energy state, or if there's a possibility to descend even further. There's a chance we might be in what's termed a false vacuum state, with the genuine vacuum or the absolute lowest energy state either nearing zero, or perhaps even reaching or surpassing it. Transitioning from our existing state to this potential state could trigger a cataclysmic event that reshapes the universe, a dreaded phenomenon termed vacuum decay. Such a transition would have dire consequences for our existence. Photons would acquire mass, the electromagnetic force would be confined to limited distances, and the majority of the sunlight from our sun would be obstructed from reaching Earth. In envisioning this as the epitome of genuine nothingness, it might be the perfect situation that preserves the laws of physics, albeit with some modifications. If one could attain the universe's true foundational state, whatever its nature, and purge all matter, energy, radiation, space-time distortions, and fluctuations, what remains would be the pinnacle of material emptiness. There would still be a backdrop for the universe's events, but it would be devoid of actors. The play would lack characters, a storyline, and a setting, yet the expansive void of material emptiness would still offer a platform. The cosmic vacuum would be at its ultimate low, rendering it impossible to derive any work, energy, or tangible particles, or antiparticles, from it. However, for some, this scenario still resonates as something, given that the constructs of space, time, and governing principles remain intact. The fourth interpretation of nothing for scientists is the idea that true nothingness is achieved only when the entire universe and its governing laws are eradicated. This is the most radical notion, a perspective that ventures beyond the confines of reality, transcending space, time, and even the realm of physics, to envision an ultimate form of void. We can think of eliminating everything conceivable, the dimensions of space, the continuum of time, and the foundational principles that dictate reality. Within the domain of physics, there's no framework to define this. It represents an absolute philosophical void. From a physics standpoint, this poses a dilemma. Such a form of void is incomprehensible. We'd be forced to postulate the existence of a state that can prevail beyond the boundaries of space and time, and from this theoretical, perfect void, space-time, and the laws overseeing all known physical phenomena could potentially originate. Regrettably, we're uncertain if this train of thought holds any tangible significance. It might just be a testament to our ability to conceptualize scenarios beyond our tangible reality, without any real-world relevance. Venturing down this path immediately presents a plethora of questions, all without clear resolutions. These questions encompass: how can space-time manifest in a specific place or moment when concepts like space, for positioning, or time, for moments, don't exist? Is it even feasible to conceptualize something as external to the universe without space, or commencing without time? From what origin would the principles that dictate particle behaviors and their interactions emerge? This ultimate notion of nothingness, though it might resonate as the most philosophically complete, might lack any real essence. It might merely be a conceptual framework shaped by our limited human understanding. When scientists discuss the concept of nothing, they often miscommunicate, assuming their interpretation of nothing is the universally accepted one. However, there's no unanimous agreement. Words can be open to interpretation, and the notion of nothingness varies depending on the context and individual. The phrase, "something from nothing," might refer to the emergence of a fundamental entity where none previously existed. But not all would concur that it sprouted from nothing. Each of the four outlined definitions holds its own merit, but it's crucial to discern the intended meaning when someone references their specific version of nothingness. Every definition has its distinct boundaries and applicability, relevant to various physical challenges, from the genesis of matter to the mysteries of dark energy, cosmic inflation, and the inherent energy of space. However, there's an inherent limitation. These ideas are all products of human cognition. Everything we're aware of undoubtedly originated from nothing. The challenge lies in deciphering the process. The elements we understand, like atoms, celestial bodies, and living things, comprise less than 5% of the universe we know. Around 25% is dark matter, and 70% is dark energy. Both are undetectable. This is odd, suggesting our lived experiences capture only a small part of the full reality. Yet, it's even more perplexing. We're largely uncertain about what dark matter and energy are, although we're fairly confident they're real. So what's known? Dark matter is essential for galaxies to form. When we analyzed the universe's structure, it became evident that there's an insufficient amount of regular matter. The gravitational force of visible matter isn't potent enough to create galaxies or complex systems. Stars would likely be dispersed randomly rather than forming galaxies. Thus, we're certain there's another component that neither emits nor reflects light. This dark matter can be indirectly observed. Areas with high concentrations bend light that passes close by, so we're sure it interacts with gravity. Currently, we have more hypotheses about what dark energy isn't than what it is. We know dark matter isn't just ordinary matter without stars, as it would emit detectable particles. It's not antimatter, as antimatter emits unique gamma rays when reacting with regular matter. It's also not black holes, compact objects that have a violent impact on their surroundings, while dark matter seems dispersed. Essentially, we're sure of a few things. Something exists. It interacts with gravity. There's a lot of it. Dark matter is likely a complex exotic particle that doesn't interact with light and matter in a way we understand. Dark energy is even more enigmatic. We can't detect it, measure it, or taste it, but its effects are clearly visible. In 1929, Edward Hubble studied how light wavelengths from distant galaxies shift towards the red end of the spectrum as they travel through space. He found that fainter, more distant galaxies showed more redshift, closer ones, less so. Hubble concluded this was because the universe is expanding. The redshift happens because light wavelengths stretch as the universe expands. More recent findings indicate that the universe's expansion is accelerating. Previously, it was believed that gravity would slow down, or even reverse this expansion. Space doesn't change its properties as it expands. There's just more of it. New space is constantly being created everywhere. Galaxies are tightly bound clusters held together by gravity, so we don't experience this expansion in our daily lives, but we see it everywhere. Wherever there's empty space in the universe, more is forming every second. So dark energy seems to be some kind of energy intrinsic to empty space. Energy that's stronger than anything else we know and keeps getting stronger. Empty space has more energy than everything else in the universe combined. We have multiple theories about what dark energy might be. One theory is that dark energy is not a thing, but a property of space. Empty space isn't nothing. It has its own energy. It can generate more space and is quite active. So, as the universe expands, it could be that just more and more space appears, leading to a faster expanding universe. This theory is similar to an idea Einstein had in 1917, the concept of a cosmological constant, a force that counteracts gravity. The only issue is that when we tried to calculate this energy, the result was so incorrect and strange that it only added to the confusion. Another theory proposes that empty space is teeming with brief, virtual particles that continually pop in and out, adding to dark energy. Or maybe dark energy is an unknown kind of dynamic energy fluid or field that permeates the entire universe, but has effects contrary to those of standard matter and energy. But if it exists, we don't know how or where or how we could detect it. So there are still many questions to answer. Our theories about dark matter and dark energy are still just that, theories. On one hand, this is frustrating. On the other hand, this is frontier science, making it very exciting. It shows us that no matter how much we think we understand, we are still very much primates with advanced technology on a small, fragile planet in space, looking at the sky and wondering how our universe functions. There is so much more to discover, and that's fantastic. Galaxies are massive assemblies of stars that fill the universe. Counting them presents a formidable challenge for several reasons. First, the sheer number of galaxies, which can run into the billions, makes the task arduous. Second, the limitations of observational equipment add another layer of complexity. For the best results, telescopes need a large aperture and should ideally be located above Earth's atmosphere to avoid optical distortions. One example that highlights these challenges is a composite image created from 10 years of photos taken by a space telescope. This image, known as the Extreme Deep Field, XDF, was generated from observations of a tiny patch of sky over a total of 50 days. To put its size in perspective, if one were to hold up a thumb at arm's length to cover the moon, the area of the sky covered by the XDF would be about the size of a pinhead. Despite its small size, the XDF revealed thousands of galaxies at various distances, making it one of the deepest views of the universe at that time. Given that such a small area of the sky contains thousands of galaxies, it's reasonable to speculate about the number of galaxies in the entire universe. Estimates generally range from 100 billion to 200 billion galaxies. The launch of more advanced space telescopes is expected to provide further insights into early galaxies in the universe. The space telescope that produced the XDF has been instrumental in estimating the number of galaxies. Initially launched with a flawed main mirror, the telescope was repaired and has undergone several upgrades. In one study, the telescope was pointed at what seemed to be an empty region of the sky for 10 days. The result was an image containing an estimated 3,000 faint galaxies. Subsequent upgrades to the telescope allowed for more in-depth studies. In one such study, an image known as the Ultra Deep Field revealed about 10,000 galaxies in a small area of the sky. Another study, using improved instruments, focused on a portion of the Ultra Deep Field and found approximately 5,500 galaxies, even in this narrower field of view. In summary, current estimates suggest there are around 100 billion galaxies in the universe, a number that could rise to about 200 billion as telescope technology improves. The method for making these estimates involves calculating the fraction of the sky observed and extrapolating this to the entire universe. The underlying assumption in these calculations is that the universe is uniform and lacks significant cosmic variance. This idea, known as the cosmological principle, has its origins in the general theory of relativity, which describes how gravity affects spacetime. The principle posits that, when viewed at a sufficiently large scale, the universe appears roughly the same in all directions. Support for the cosmological principle comes from observations of the cosmic microwave background, CMB, a form of radiation that dates back to the early universe. Instruments have shown that the CMB is nearly identical in every direction, supporting the idea that the universe is homogeneous and isotropic on large scales. The age of the universe, determined through observations of its expansion and the movement of galaxies away from Earth, is estimated to be around 13.82 billion years. As the universe continues to age and expand, galaxies will move further away from Earth, making them increasingly difficult to observe. Interestingly, the rate of the universe's expansion exceeds the speed of light, which doesn't violate the laws of physics, as the expansion applies to the fabric of the universe itself, not to objects within it. The acceleration of the universe's expansion introduces the concept of the observable universe, which refers to the portion of the universe that can be seen from Earth. In a time frame of 1 to 2 trillion years, some galaxies will move beyond the reach of our observational capabilities. This limitation doesn't imply that the observable universe is all that exists. It simply means that some regions will be unobservable due to the finite speed of light. Galaxies are not static, they undergo changes over time. For example, the Milky Way is on a collision course with the Andromeda Galaxy, and this merger is expected to occur in about 4 billion years. Following this, other galaxies in our local group are likely to merge as well. Future inhabitants of such a merged galaxy would find themselves in a much darker universe, devoid of evidence for the existence of other galaxies or cosmic expansion. Theories about the early universe suggest the possibility of multiple universes, each potentially having different rates of expansion, types of matter, and physical laws. These other universes could also contain galaxies, but this remains speculative as current observational methods cannot confirm their existence. Therefore, the actual number of galaxies could be much higher than current estimates if multiple universes exist. Advancements in telescope technology, such as the James Webb Space Telescope, are expected to refine our estimates of the number of galaxies. Current telescopes can observe galaxies that formed about 450 million years after the Big Bang. The James Webb Space Telescope is expected to look back as far as 200 million years after the Big Bang. However, the overall count of galaxies is not expected to change significantly, suggesting that the current estimate of around 200 billion galaxies in our observable universe is likely accurate. While counting galaxies is a fascinating endeavor, the primary focus of astronomers is to understand how galaxies reveal information about the formation of the universe. Galaxies serve as indicators of how matter in the universe is organized on a large scale. Advanced telescopes will allow for the study of the universe's earliest galaxies, thereby enhancing our understanding of how galaxies have evolved over time. This will include insights into the formation of elements heavier than hydrogen and the processes behind galaxy mergers. One of the key questions in astronomy concerns the role of dark matter in the formation of galaxies. Although most of the universe is made up of dark matter, constituting about 80% of its mass, it doesn't emit light or energy, making it invisible. Studies have indicated that there's more mass in galaxies than what can be observed. Computational models suggest that dark matter serves as a kind of scaffolding on which visible matter accumulates to form stars and galaxies. The James Webb Space Telescope is expected to provide more insights into this, thereby enriching our understanding of galaxy formation and, indirectly, our estimates of the number of galaxies. One of the most intriguing and fundamental questions that has captivated the minds of cosmologists, astronomers, and even the general public is, where did the Big Bang happen? Addressing this question delves deep into our understanding of the universe's origins and challenges our perceptions of space and time. The answer, both profound and conceptually challenging, reshapes our perspective on the vast cosmos and our place within it. A widespread misunderstanding surrounding the Big Bang is the idea that it functioned like a typical explosion, emanating from a singular, infinitesimally small point in space. Many envision it as a firecracker moment, where all matter and energy burst forth from a central location. This model, while visually compelling, is not in line with our current understanding of the event. Instead of a localized explosion, the Big Bang represents a simultaneous expansion of space everywhere. This crucial distinction is backed by a wealth of astronomical observations and theoretical frameworks, challenging our intuitive grasp of the universe's inception. If we were to adhere to the firecracker model, our astronomical observations would present a very different picture of the universe. We would expect to identify a central point from which all galaxies are moving away. Furthermore, galaxies situated on the opposite side of this hypothetical center from us would appear to be receding at an even more rapid pace, given the additional distance they would have had to traverse since the Big Bang. This would create a sort of gradient in the velocities of galaxies based on their positions relative to this center. Yet what we observe through telescopes paints a different story. No matter which direction we look, galaxies seem to be moving away from us at rates proportional to their distances, suggesting a uniform expansion. This observation challenges the notion of a singular explosion point, and instead supports the idea that every point in the universe is expanding away from every other point. The uniform motion of galaxies presents two potential theories. One suggests that Earth occupies a unique position, central to the aftermath of the Big Bang, providing us a singular perspective from which to observe the universe's expansion. The other, more widely accepted by scientists, proposes an entirely different scenario. To understand this second scenario, it's essential to differentiate between the observable universe and the entire universe. The observable universe is the part of the cosmos visible from Earth, constrained by the speed of light and the universe's age. Centered around Earth, this sphere spans roughly 14 billion light-years in every direction. It lets us see objects whose light has taken that long to reach us. However, considering the universe's ongoing expansion since the Big Bang, the actual radius of the observable universe is closer to 46 billion light-years. This accounts for the space that has expanded as the light traveled to Earth. Beyond this observable realm, the entire universe extends much further, and its true size is a subject of ongoing scientific inquiry and speculation. Preliminary evidence, derived from the study of ancient light or cosmic background radiation left over from the early stages of the universe, suggests that the entire universe is immensely larger than the portion we can observe. The radius of the whole universe is estimated to be at least 500 times that of the observable universe. When considering the volume, this implies that the entire universe could be a staggering 125 million times larger than the observable universe, if not more. This vast expanse contains regions that are currently beyond our observational capabilities, holding mysteries and wonders that we are yet to uncover and understand. The concept of infinity is a challenging one, especially when applied to the vastness of the universe. When we say the universe is infinite, it challenges our everyday understanding of space and time. This notion of infinity implies that there are no boundaries, no edges, and no center to the universe. It stretches endlessly in every direction. The observable universe, the part we can see and study, is just a tiny fraction of this infinite expanse. As our technology advances and our telescopes peer further into the depths of space, the boundary of the observable universe will shift, revealing more galaxies, stars, and cosmic phenomena. Yet, no matter how much we expand our observational capabilities, we will never be able to see the entirety of an infinite universe. This continuous expansion of the universe is not like the explosion of a bomb, where fragments fly outwards from a central point. Instead, it's the very fabric of space itself that's stretching. Every galaxy is moving away from every other galaxy, making it seem as if we're at the center. But this is an illusion. An observer in a galaxy billions of light years away would see the same thing. Galaxies moving away in every direction. The idea that the Big Bang occurred everywhere might seem counterintuitive. If we were to imagine the universe as an infinite rubber sheet, the Big Bang would be like stretching that sheet in every direction. Every point on the sheet moves away from every other point, but there's no single point of origin for the movement. This perspective reshapes our understanding of our place in the cosmos. It humbles us, reminding us of our tiny existence in the vastness of the universe, while also highlighting the incredible interconnectedness of everything. The realization that every point in the universe can be seen as the center is not just a scientific observation. It's a philosophical and existential insight that underscores the profound mysteries of our universe and our quest to understand them. The concept of general relativity allows for the universe to exist in one of three possible shapes. It could be flat like a sheet, spherical like a ball, or resemble a saddle. The geometry of the universe isn't just a theoretical concern, it has profound implications for the universe's ultimate fate. The shape of the universe can reveal important information about its past and what might happen to it in the future. Whether the universe will continue to expand indefinitely or eventually contract, and whether it is limited or limitless, are all questions closely tied to its shape. The overall architecture of the universe hinges on two key elements: how dense it is and how fast it is expanding. So, is the universe closed, open, or flat? About 2/3 of the universe is made up of dark energy, and just over a quarter is dark matter. The rest is regular matter, like planets and stars. The concept of density of the universe refers to how much of this matter and energy is contained in a given volume. If the universe is dense enough for its gravitational pull to counterbalance its expansion, it will take a spherical form. This is known as a closed universe. Interestingly, this kind of universe would be finite, but without any boundaries, allowing for endless travel within it. On the flip side, if the universe isn't dense enough to counteract its expansion, it will take on a shape similar to a saddle. This is known as an open universe. According to the most credible scientific data, the most likely shape of the universe is flat. In this scenario, the density is just right, allowing the universe to expand in all directions without curving. This could be comforting to those who find the roundness of Earth disheartening. What does it mean when we say the universe is flat? This flatness isn't the 2D type we're familiar with in daily life, but it can be understood through some comparisons. Imagine you're in one corner of a square room. Walk 10 feet to the next corner along the wall, then make a 90-degree turn. Walk another 10 feet, make another 90-degree turn, and repeat this twice more. You'll end up back at your starting point, completing a square. This is the typical Euclidean geometry we learned in school, and adding an extra dimension to it gives you a flat universe. Now let's consider a different scenario that represents a positively curved or closed universe. Start at the equator on Earth and walk to the North Pole. Make a 90-degree turn and walk back to the equator. Make another 90-degree turn and return to your original position. In the flat universe scenario, you needed 4 turns to return to the starting point, but in the closed universe, you only needed 3. If you're still puzzled, here's another way to think about it. In a flat universe, 2 rockets flying side by side will stay parallel forever. This contrasts with a closed universe, where the rockets' paths will eventually curve and meet again at the starting point. In an open, negatively curved universe, the rockets will drift apart and never intersect again. A significant hint about the universe's shape can be found in the cosmic microwave background, CMB, which is the residual heat from the Big Bang that we can detect from every direction. Over the years, researchers have studied temperature variations in the CMB, essentially using large-scale trigonometry, and have discovered almost no curvature. The idea of a flat universe is central to the prevailing cosmological theory, often referred to as the lambda cold dark matter model. However, in 2019, a study suggested that CMB measurements from a space observatory might point to a closed universe. This conclusion was drawn from analyzing gravitational lensing, which is the deflection of CMB light due to the gravitational pull of matter. The observed amount of this lensing was higher than what the standard model predicted. By not assuming a flat universe, the observed deviation can be reconciled. While this observation was noted by the same team that conducted the Space Observatory's measurements, they didn't consider it highly significant. Some experts believe that this variance might just be a random anomaly. In large datasets, it's common to find unexpected results. However, the importance of these findings shouldn't be overlooked. While it's not a direct claim that the universe is closed, it suggests that there might be something crucial we're missing. Recognizing this, some researchers have labeled it a cosmological crisis. Assuming a closed universe could lead to conflicts with other datasets, making it a challenging proposition. If proven correct, the idea of a closed universe would upend years of established astronomical research. However, apart from this one set of data, there's no other evidence to question the prevailing view that the universe is flat. Other CMB measurements, such as those from telescopes in Chile and other probes, all align with a flat universe. Additional data, particularly from baryon acoustic oscillations, patterns left on galaxies by ancient sound waves following the Big Bang, also support the flatness hypothesis. Given the overwhelming evidence in favor of a flat universe, most scientists would be skeptical of a single, contradictory finding. While the study suggesting a closed universe does highlight an interesting feature in the data that leans toward positive curvature, additional data consistently supports a flat universe. In a recent paper, researchers combined multiple datasets with the data in question and found no deviation from flatness, suggesting that the observed anomaly could be a statistical fluctuation. Other studies have reached similar conclusions, indicating that there's no need to revise the current cosmological model. For the time being, it seems the universe behaves like a 3-dimensional sheet of paper. While not everyone is convinced it's definitively flat, that's how it appears based on our current observations. It's important to remember that our viewpoint is restricted to the observable universe, so there might be aspects we're not aware of. If the universe does have curvature, it would have to be so immense that the 93 billion light-years we can observe don't provide a large enough sample to detect it. To draw an earthly analogy, it's as if we're standing in a foggy environment, only able to see a small, flat area, while the true shape of the Earth remains hidden beyond the horizon. In saying the universe is flat, what's really meant is that the portion we can observe is consistent with being part of a flat 3-dimensional space. In a perfect scenario, determining the universe's age would involve numerous independent evidences, all pointing to the same conclusion. However, we actually have just two reliable methods, with one being more compelling than the other. The stronger method examines the universe's current state of expansion and cooling, suggesting it was denser and hotter in the past. As we trace back in time, we find that the universe was more compact, leading to higher concentrations of matter and shorter wavelengths for photons. These wavelengths have been elongated due to the universe's expansion over time. The energy and temperature of a photon are dictated by its wavelength, so shorter wavelengths correspond to higher energy and temperature. Going back far enough, we eventually reach the initial conditions of the hot Big Bang. Importantly, there is a definable beginning to this hot phase. If we were to extrapolate infinitely backward, we would hit a singularity where our current understanding of physics fails. However, modern theories propose that an inflationary period existed before the hot Big Bang, although its duration is not well defined. Therefore, when we talk about the universe's age, we mean the time elapsed since this hot Big Bang phase commenced. According to general relativity, our universe has specific characteristics. It is uniformly dense at large scales, has consistent laws and properties throughout, is the same in every direction, and the Big Bang occurred everywhere at once. These characteristics create a unique link between the universe's age and its history of expansion. To determine this, we rely on various observations. These include direct measurements of the brightness and distance of celestial objects, which help us build the cosmic distance ladder. We also use observations of large-scale structures, galaxy clusters, and baryon acoustic oscillations, as well as fluctuations in the cosmic microwave background, which offers a snapshot of the universe when it was just 380,000 years old. Combining all these observations, we find that the universe is primarily composed of 68% dark energy, 27% dark matter, 4.9% ordinary matter, around 0.1% neutrinos, and about 0.01% radiation. Using this composition, we can trace back the universe's expansion history and calculate its age to be 13.81 billion years, with a 99.1% level of confidence. Although we have various datasets, they all essentially use the same approach. Each data set on its own is not sufficient to provide a conclusive answer, but their collective agreement gives us a consistent picture. For instance, if the universe were made entirely of normal matter, it would be only 10 billion years old. If it were 5% normal matter with a different Hubble constant, its age could be as much as 16 billion years. Given the current data, we can confidently say the universe is 13.81 billion years old. While this is mainly one method, it is the most comprehensive and reliable, backed by multiple pieces of evidence. However, there's a secondary method that serves as a useful validation. This involves understanding the life cycles of stars, specifically how they maintain a certain brightness and color while fusing hydrogen into helium. This changes when their cores run out of fuel. By observing this turn-off point in star clusters, we can estimate their age. The oldest such clusters suggest an age of around 13.2 billion years, albeit with a significant margin of error. Ages above 14 billion years are now considered rare, although they were more commonly cited in the 1990s before our understanding of stellar evolution improved. In summary, both cosmic history and local star measurements indicate that the universe's age lies between 13 and 14 billion years. It's plausible that the actual age could range between 13.5 and 14.1 billion years, but ages like 13.0 or 15.0 billion years can be confidently ruled out. Thus, we can assert with high certainty that the universe is 13.8 billion years old, and this is how we've reached that conclusion. The universe has been around for 13.8 billion years, a figure we've determined through various scientific methods. However, this is the time that has elapsed from our vantage point on Earth. Time is relative, so what does this mean for observers in different parts of the cosmos? Everything we observe in our galaxy also seems to be 13.8 billion years old, with some exceptions. The celestial bodies we see in the sky aren't exactly the same age as Earth. Due to the finite speed of light, when we observe a star 100 light-years away, we're actually seeing it as it was a century ago. But when you consider that in the context of 13.8 billion years, Even a star at the other end of our galaxy, 100,000 light-years away, doesn't make much of a difference in age. However, when we start observing other galaxies, the situation changes. As we peer deeper into space, we encounter galaxies that date back to when the universe was less than 1 billion years old, a mere fraction of its current age. If our observational technology were advanced enough, we'd see stars composed almost entirely of hydrogen and helium, the elements formed in the Big Bang. There would be a lack of elements like carbon, oxygen, and iron, which are necessary for the formation of rocky planets and life. It's crucial to note that we're observing these galaxies as they were in the past, not as they are now. This is a matter of our perspective. We're the ones looking back through time. For an observer in a far-off galaxy or billions of light-years away, we would be the ones who seem to exist in the past. To someone 100 light-years away, Earth would appear pre-technological, without nuclear bombs or computers. To an observer in a galaxy 1 billion light-years away, our sun would seem younger and less bright. Earth would only have simple single-celled life, and our continents would be largely barren, covered in ice and soil. Most unsettlingly, for someone observing us from the farthest galaxies we can see, not only would our Earth and Sun be non-existent, but likely the Milky Way itself would also not have formed. Instead, we'd be a collection of gas clouds and proto-galaxies, still in the process of merging into the spiral formation that would eventually become our home galaxy. Only the most ancient globular clusters, now residing in our galaxy's halo, would be present, filled with hot, young, blue stars that have long since disappeared. For any observer, whether they're on a different star in another galaxy or at the opposite end of the universe, their perception of the universe would closely mirror ours. A universe that is 13.8 billion years old as of now. A universe where, no matter which direction they gaze, they seem to be looking further back in time. A universe where the cosmic microwave background has cooled to a temperature of 2.725 K today. A universe where the cosmic web looks virtually identical to the one we observe. And a universe where, if they were to look in our direction, they would see us as far back in time as we see them. Given all this, one might think there's some sort of universal clock, right? While it may seem so, that's not exactly true. What is accurate is that the Big Bang happened 13.8 billion years ago everywhere in space, and this holds true from the perspective of all galaxies. But what if there were galaxies moving not at hundreds or thousands of kilometers per second, relative to the cosmic microwave background, but at speeds approaching that of light? Just as time dilates for objects moving near the speed of light on Earth, be it a particle, a train, or a human, if there were a planet, star, or galaxy moving near light speed for an extended period, it would be considerably younger than the rest of the universe. Consider this hypothetical. A galaxy was accelerated to 99% the speed of light 1 billion years after the Big Bang due to multiple gravitational interactions. While 12.8 billion years have elapsed for us since then, only 1.8 billion years would have passed for that particular galaxy. It would appear smaller, less developed, bluer, and arrested in its evolution compared to galaxies like ours. So for nearly all observers, the universe would look consistent, with the same amount of time having passed, and the universe exhibiting the same large-scale characteristics. However, for a select few observers, those who have been moving close to the speed of light relative to the cosmic microwave background, the universe would appear quite odd. Once they decelerate and come to a stop relative to the CMB, they would find themselves as youngsters in an inexplicably aged universe. The notion that 13.8 billion years have passed since the Big Bang is a universal truth for everyone within our observable universe. However, if you were moving at speeds close to that of light, you might find that hard to accept. Tales of journeying to the past and future have always intrigued us, yet the feasibility of time travel is a complex issue that delves deep into what physicists mean when they talk about time. Contemporary physics tells us that time is one of the universe's most enigmatic features, even though it might initially appear simple. Einstein transformed our grasp of this concept, but even with this new framework, some researchers still debate whether time truly exists, or is just a persistently stubborn illusion, as Einstein once termed it. Regardless of what time actually is, both scientists and authors have devised intriguing methods to potentially navigate through it in unconventional ways. Although H.G. Wells mentioned it in his 1895 novel, The Time Machine, The real science behind time travel didn't emerge until the 20th century, largely due to Albert Einstein's 1915 theory of general relativity. This theory portrays the universe's structure as a four-dimensional spacetime, incorporating three spatial dimensions and one time dimension. Supported by extensive experiments over the past century, this theory posits that gravity occurs due to the warping of spacetime by matter. Essentially, a specific arrangement of matter can significantly alter the spacetime fabric of the universe. A remarkable implication of relativity is the phenomenon of time dilation, where motion can cause time to pass differently. This is most vividly demonstrated in the well-known twin paradox. In this form of time travel, you can accelerate into the future, but reversing the journey is generally not possible. In 1937, W.J. van Stockham, a Scottish physicist, was the first to use general relativity in a manner that suggested time travel might be feasible. He applied the equations of general relativity to a scenario involving an infinitely long, extremely dense rotating cylinder, somewhat akin to an eternal barbershop pole. The rotation of this massive entity creates a frame-dragging effect, pulling spacetime with it. Van Stockham discovered that this could lead to a closed time-like curve, essentially a loop in spacetime that permits time travel. You could embark on a spaceship journey that returns you to the exact moment you left. Although this was a captivating finding, it was largely seen as a theoretical construct and not a practical concern. However, a more contentious interpretation was soon to follow. In 1949, mathematician Kurt Gödel, a colleague and friend of Einstein's at Princeton University's Institute for Advanced Study, explored a scenario where the entire universe is rotating. According to Gödel's calculations, if the universe were rotating, time travel would be permitted by the equations of general relativity. A rotating universe could act as a time machine in itself. If the universe were indeed rotating, there would be observable signs, such as the bending of light beams. However, current evidence overwhelmingly suggests that the universe is not rotating in this manner. Therefore, this particular model rules out time travel. Yet, the fact that objects in the universe do rotate keeps the possibility alive. In 1963, Roy Kerr, a mathematician from New Zealand, employed field equations to study a spinning black hole, known as a Kerr black hole. He discovered that such a black hole could theoretically allow a route through a wormhole, bypassing the central singularity and exiting on the other side. This idea also paved the way for closed time-like curves, a concept later recognized by theoretical physicist Kip Thorne. In the early 1980s, while author Carl Sagan was working on his 1985 book Contact, he consulted Kip Thorne about the physics of time travel. This prompted Thorne to explore the idea of utilizing a black hole for time travel purposes. Alongside physicist Sung-Won Kim, Thorne theorized that a black hole connected to a wormhole, kept open by some form of negative energy, could exist in theory. However, the mere existence of a wormhole doesn't automatically make it a time machine. Let's hypothesize that one end of the wormhole could be moved, referred to as the movable end. If this movable end is placed on a spaceship and propelled into space at nearly the speed of light, time dilation would occur. The time experienced by the movable end would be significantly less than that experienced by the stationary end. For instance, if you move the movable end 5,000 years into Earth's future, but it only ages 5 years, you would depart in 2010 AD and arrive in 7010 AD. Yet, if you traverse through the movable end, you would actually emerge from the stationary end in 2015 AD, as only 5 years have elapsed on Earth. How is this possible? The reality is that the two ends of the wormhole are intrinsically linked. Regardless of their spatial separation, they are essentially close to each other in spacetime. Since the movable end is only 5 years older than when it departed, entering it would take you back to the corresponding point on the stationary end. Similarly, if someone from Earth in 2015 AD were to enter the stationary end, they would exit from the movable end in 7010 AD. If someone entered the wormhole in 2012 AD, they would find themselves on the spaceship during its journey and so forth. While this is the most plausible scientific explanation for a time machine, there are still unresolved issues. The existence of wormholes and negative energy is still uncertain, and even if they do exist, we don't know how to assemble them in this manner. Nonetheless, the theory remains tantalizingly feasible. The universe, vast and mysterious, can be understood through a set of parameters that provide insights into its composition and evolution. These parameters, ranging from the nature of dark matter to the intricacies of light waves, offer a comprehensive view of the cosmos. By delving into these variables, we can explore the early stages of the universe, the formation of galaxies, and the fundamental forces at play. The first three variables give us insights into the universe's composition, which we can think of as slices of a pie chart. The first variable indicates that normal matter, or atoms, make up only 5% of the universe. The second variable pertains to dark matter, an unknown fundamental particle constituting 25% of the universe. Intriguingly, the amount of dark matter calculated from the tiny temperature variations in the cosmic microwave background, CMB, aligns with what we observe from the movements of stars and galaxies. The CMB-based calculation is notably more accurate. Additionally, the CMB originates from a time when the universe had cooled sufficiently to release photons from the hot plasma that had confined them for hundreds of thousands of years post-Big Bang. This allows us to confirm that dark matter was present in the early universe. Moreover, atoms, the building blocks of our existence, make up only 1/6 of the universe's total mass. The third variable is the cosmological constant, the enigmatic dark energy responsible for the universe's accelerating expansion, making up 70% of the universe's total matter and energy. The fourth variable is optical depth, which measures the universe's opacity to photons. This is the most astrophysical among all the standard cosmological model parameters. It encapsulates our limited understanding of the intricate processes involved in the creation and subsequent detonation of the first stars and the genesis of the initial galaxies. The intense radiation from these early celestial bodies broke hydrogen atoms in the universe into protons and electrons, leading to the universe's reionization. During this event, 58% of the CMB photons, which had been freed during the decoupling era, were scattered again. To draw an analogy, it's as if a light mist appeared in what had been a clear universe, slightly reducing visibility. Interestingly, measuring the universe's optical depth requires assessing the CMB's polarization. Polarization, along with intensity and wavelength, is one of the three attributes of a light wave. Polarization defines the oscillation direction of a light wave. For instance, light bouncing off your car's hood is horizontally polarized. Polarized sunglasses are designed to block this specific oscillation and the glare it causes. Likewise, the electrons released during reionization scattered and polarized the CMB photons. If you were to observe the CMB through polarized sunglasses, you'd notice a subtle difference in its appearance. The final two parameters focus on the tiny fluctuations that serve as the foundation for all the structures we currently see in the universe. If we had a comprehensive model of the universe that started with minuscule quantum fluctuations and accurately predicted fluctuations in matter within spheres of 25 million light-years, we could discard one of these two parameters. Regrettably, although we possess a highly effective model for tracing the universe's evolution, we still lack a complete understanding of all the interconnections, necessitating this parameter. This parameter is known as the primordial power spectrum, and it outlines the variations in the universe's density across three-dimensional space. In the universe's infancy, these fluctuations were minor, but as the universe grew, these variations in density became magnified. In regions where the early universe was slightly denser, matter continued to aggregate, resulting in what we now recognize as galaxies or galaxy clusters. In less dense areas, we observe virtually nothing. The last parameter, termed the scalar spectral index, is the most complex to comprehend, but also offers the most insightful glimpse into the universe's origins. It informs us how the initial fluctuations, the minuscule variations in energy in the young universe, are related to angular scale. To make this easier to understand, consider a musical analogy. This ultimate parameter helps us differentiate between white noise and, for instance, pink noise, where lower frequencies, akin to larger angular scales, are somewhat louder than higher frequencies, akin to smaller angular scales. Through the CMB, we discover that the initial fluctuations were marginally more pronounced at larger angular scales compared to smaller ones. In simpler terms, the original cosmic noise leans slightly toward the pink side. Armed with these 6 parameters, we can calculate not only the properties of the CMB, but also any other cosmological measurement we wish to undertake. For instance, we can determine the universe's age to be 13.8 billion years, with a margin of error of 40 million years. The most restrictive observation comes from the CMB anisotropy, which are the subtle temperature variations. Nevertheless, the standard cosmological model aligns well with all observations across various scientific disciplines, including physics and astronomy. In summary, regardless of how we examine the universe, be it through galaxy surveys, exploding stars, the prevalence of light elements, the velocities of galaxies, or the CMB, we only require the aforementioned 6 parameters and understood physical processes to depict the universe we see. What does this level of quantitative simplicity imply? It signifies that we grasp how the universe's components interlock to create a unified whole. We comprehend certain profound relationships in nature. It also means we can be proven incorrect, not by alternative theories, but by a more accurate quantitative model that accounts for more natural phenomena. Few systems that scientists study can be described with such simplicity, completeness, and precision. We are lucky that the observable universe is one such system. The narrative of how the universe evolved from the Big Bang to its current state, filled with cosmic structures like galaxies, stars, and planets, is a story that unites us all. From Earth's vantage point, nearly 2/3 of the universe's history had passed before the Sun and Earth came into existence. Interestingly, life on Earth may have emerged as far back as 4.4 billion years ago, raising questions about whether life predates our planet and how far back in time it could go. When could the universe have had enough heavy elements to support the formation of planets and potentially life? Even if we limit our inquiry to life forms similar to those on Earth, the timeline for the possibility of life extends further back than one might think. We can't trace back to the universe's absolute beginning. Right after the Big Bang, the universe was devoid of stars, galaxies, and even atoms. It started as a nearly homogeneous mixture of matter, antimatter, and radiation. The regions with slightly higher density were only about 0.003% denser than the average, meaning a significant amount of gravitational collapse would be needed to form something as dense as a planet, which is about a factor of 10 to the power of 30 denser than the universe's average density. However, the universe has all the time it needs to make this happen. After roughly the first second, most of the antimatter and matter had annihilated each other, leaving behind a small amount of protons, neutrons, and electrons, along with a sea of neutrinos and photons. Around 3 to 4 minutes post-Big Bang, these protons and neutrons had combined to form stable atomic nuclei, but these were almost entirely hydrogen and helium isotopes. It wasn't until about 380,000 years later, when the universe had cooled down sufficiently, that electrons could bind to these nuclei to form neutral atoms. Even then, the conditions for life or even rocky planets were not yet met, as only hydrogen and helium atoms were available. Gravitational collapse is a transformative process that, over time, alters the universe's structure. Although it starts off slowly, its effects are cumulative. The denser a region in space becomes, the more effective it is at pulling in additional matter. Simulations suggest that the first stars could have formed around 50 to 100 million years post-Big Bang. These initial stars would be composed solely of hydrogen and helium, and could reach enormous sizes, hundreds or even 1,000 times the mass of our Sun. Such massive stars would have a short lifespan, dying within 1 or 2 million years. The death of these stars is a monumental event, given the fusion processes they undergo. All stars convert hydrogen into helium, but the most massive ones go further, fusing helium into carbon, then carbon into other elements like oxygen, neon, magnesium, silicon, and sulfur, and so on until they reach iron, nickel, and cobalt. At this point, the core collapses, resulting in a supernova explosion that disperses heavy elements throughout the universe. This enriches the interstellar medium and sets the stage for the formation of rocky planets and organic molecules. As more stars live, burn out, and explode, the next generation becomes increasingly enriched with heavy elements. Many supernovae result in neutron stars, and the collision of these neutron stars produces even heavier elements. This leads to the formation of denser rocky planets and increases the likelihood of complex organic molecules forming. We don't need the entire universe to resemble our solar system. A few generations of star life cycles in dense regions are sufficient to create conditions conducive to life. By the time the universe is 1 billion years old, we find that the most distant objects with measurable heavy element content have as much carbon as our solar system. Other heavy elements accumulate even faster. Carbon might take longer to reach high levels because it's primarily produced in stars that don't explode, unlike the ultramassive ones that do. While rocky planets don't specifically need carbon, other heavy elements suffice. Phosphorus is also created in supernovae, dispelling recent exaggerated reports of its scarcity. Likely, rocky planets began forming around the most element-rich stars when the universe was between 300 and 500 million years old. If carbon weren't essential for life as we know it, life could have started even earlier. However, for life forms like ours, a sufficient amount of carbon probably wouldn't be available until the universe was about 10% of its current age, or between 1 and 1.5 billion years old. This is later than the 3 to 4% of its current age needed for rocky planets to form. It's fascinating to consider that the universe had all the necessary elements for life except carbon, which required the life cycles of the most massive stars, similar to our Sun. If we look at Earth's history and the complexity of genomes over time, we find that the simplest forms of life could date back to 9 to 10 billion years ago, rather than 12 to 13 billion years ago. Could this imply that Earth's life originated before the planet itself? Or that life could have started billions of years earlier elsewhere, but took extra time to develop here? We can't say for sure. We also don't know the boundary between life and non-life, or whether life on Earth originated here, on a different planet, or even in the depths of interstellar space without a planet. What's truly captivating is that the elemental building blocks for life existed shortly after the first stars formed. Carbon, the fourth most abundant element in the universe and crucial for life, was the last to reach the necessary abundance. Rocky planets could have formed as early as 500 million years after the Big Bang. Once carbon became abundant, around 1 to 1.5 billion years post-Big Bang, the conditions for the formation of organic molecules and the initial steps toward life became inevitable. Life as we understand it could have started when the universe was just 1/10 of its current age. The question of whether we are alone in the universe has puzzled humanity for ages, and despite technological progress, no definitive evidence of extraterrestrial life has been found. Organizations like the Search for Extraterrestrial Intelligence, SETI Institute, have been scanning the heavens for radio signals since 1984. Space telescopes like Kepler have identified thousands of exoplanets, and the James Webb Space Telescope has recently captured its first direct image of an exoplanet. One of the most intriguing signals ever received was the WOW signal in 1977, detected by a radio telescope at Ohio State University. Although initially considered a potential sign of extraterrestrial intelligence, most experts now think it's unlikely to be of alien origin. A study published in May 2022 in the International Journal of Astrobiology suggested that the signal might have originated from a Sun-like star about 1,800 light-years away. Two key concepts related to the search for extraterrestrial life are the Fermi paradox and the Drake equation. The Fermi paradox, coined by physicist Enrico Fermi, questions why we haven't yet encountered any advanced alien civilizations, given the age and size of the universe. Some students of astronomy and physics, like Harshini Sunil, find the paradox compelling because it challenges the likelihood of advanced life existing elsewhere in our galaxy. On the other hand, the Drake equation, formulated by Frank Drake, offers a more hopeful perspective. It attempts to estimate the number of civilizations in the universe that could communicate with us by considering various factors, including astronomical, biological, and technological elements. The Drake equation's variables are largely speculative, leading to a wide range of estimates for the number of technological civilizations, from just us to as many as 1 million. Some experts in astrobiology view the equation as both a sobering and inspiring tool. It provides a realistic framework for the search for extraterrestrial life, reminding researchers that not every signal will be from an alien civilization. However, the equation also instills hope, as the mere existence of human civilization suggests the potential for others. The question of whether we are alone in the universe remains unanswered. While we haven't yet received a definitive signal from extraterrestrial beings or developed spacecraft capable of interstellar travel, there are numerous planets and moons within our own solar system that could potentially harbor microbial life. So, where should we focus our search for alien life? Some experts find it hard to decide between the protected regions of Mars and the ocean floors of moons, like Enceladus and Europa, as the most promising locations for life within our solar system. Ongoing research on Earth's extreme environments shows that life can exist in unexpected places, suggesting that similar habitats might exist on Mars or beneath its surface. Additionally, the presence of liquid water in contact with rocky seafloors on these moons offers exciting possibilities for life as we understand it. Planets, dwarf planets, and moons may have internal processes that could support life, and Earth's deep-sea hydrothermal vents could have equivalents in extraterrestrial oceans. NASA's Mars rovers, Curiosity and Perseverance, are actively exploring Gale Crater and Jezero Crater for signs of past or current life. Meanwhile, NASA is also planning and executing other missions aimed at answering the age-old question of whether we are alone in the universe. Some experts highlight the upcoming Dragonfly mission to Titan and the already operational James Webb Space Telescope as particularly promising for finding signs of life. If humanity were to discover extraterrestrial life, either intelligent or microbial, the impact on society is a subject of speculation. Some believe that such a discovery would be exhilarating, but wouldn't fundamentally alter humanity's place in the universe. The discovery would address some of the questions posed by the Fermi paradox, but wouldn't diminish the significance of human existence, which is the result of billions of years of evolution. The search for extraterrestrial life continues to be a focus of scientific inquiry. SETI is still scanning the skies for radio signals. The James Webb Space Telescope is providing groundbreaking images and data. Mars rovers are conducting on-site investigations, and plans are underway for future missions to explore the outer reaches of our solar system for signs of life. The question of whether we are alone in the universe remains unanswered. Until that question is resolved, the search for extraterrestrial life will continue to be a priority for humanity. For centuries, humans have viewed themselves as central to existence. However, scientific discoveries seem to diminish our significance. Yet perhaps we were too quick to dismiss our importance. In some ways, we might still be at the heart of the cosmos. Science also reveals that the physical laws of the universe are astonishingly calibrated for our existence. Consider the electromagnetic force. Its precise value is essential for stars to combine protons and neutrons, forming carbon, the foundation of life as we recognize it. Then there's the strong nuclear force, responsible for holding protons and neutrons together. If it were slightly more potent, our world would be dominated by hydrogen. If weaker, hydrogen would be absent. In both scenarios, familiar life wouldn't exist. Even the energy in the vacuum of space seems tailored for the emergence of intelligent beings. And that's just the beginning. In total, around 12 factors have been pinpointed as crucial for life's existence. Why does the universe seem so impeccably designed? The prevailing sentiment among physicists is that, in a way, it had to be this way. This line of thought has birthed various explanations termed as anthropic principles. In the ongoing debate about the universe and our place in it, one perspective asserts that humans are central to everything. This view suggests that the universe's precise conditions might have been intentionally designed for our existence. This could be attributed to an intelligent designer, or more likely, a fundamental property of the universe that naturally leads to the rise of intelligent life. The idea that life might inherently be a fundamental aspect of nature has been introduced, termed the life principle. However, it's noted that this idea has theological implications. Despite these theories, there's significant skepticism within the scientific community. Some find the idea that the universe was specifically designed for humans to be an unconventional and challenging notion to accept. Could it be, then, that the perspective is reversed? Another interpretation of the anthropic principle suggests that the universe is here because of our existence. There are also more grounded interpretations of the principle. These alternatives aim to rationalize why the universe seems tailor-made for us, even if it's not. Essentially, this milder version of the anthropic principle posits that since we're here to witness the universe, it must inherently support our presence. This often suggests that there might be other parts of the universe, or even distinct universes, where the laws and constants of physics vary. Thus, questioning why our universe is the way it is equates to asking why we exist in this particular region. In this context, the anthropic principle simply highlights that the only locations we could possibly inhabit are those conducive to our form of life. This argument gains traction with the potential existence of a multiverse, a concept supported by both quantum mechanics and conventional cosmology. With numerous other universes, each governed by their unique laws and constants, the enigma of our universe's precise calibration becomes moot. We exist in a universe that's perfectly suited for carbon-based existence. Yet, even if this interpretation of the anthropic principle accounts for the universe's fine-tuning, it repositions humans to a central role in our understanding of the cosmos. It's somewhat of a reversal in the scientific journey that had previously sidelined the observer. There are boundaries that even advanced technology can't surpass. We are confined to a specific region of the universe with finite resources. What portion of the universe is accessible to us, and how far can we venture? Observing the night sky might give the impression of its permanence. Stars have life cycles, but these cycles are not infinite. Consider the Milky Way, spanning up to 200,000 light-years and housing between 100 to 400 billion stars. How many new stars are formed annually? The number is surprisingly low at 3. 95% of all stars that will ever be formed already exist, and we are in the declining phase of star creation. We are entering the final stages of the universe as we understand it, as the rate of new star formation continues to decrease. But there's more to consider. The universe is expanding away from us. The Milky Way is part of a larger structure, the Local Group, which also includes the Andromeda Galaxy and over 50 dwarf galaxies. This structure spans approximately 10 million light-years. Numerous such groups form the Laniakea supercluster, one of countless superclusters. In total, the observable universe consists of around 2 trillion galaxies. Regrettably, even at the speed of light, about 94% of the galaxies currently visible to us will never be within our reach. This is a daunting realization. Why are these galaxies already inaccessible? The reason lies in the event that created galaxies, the Big Bang. Simplifying a bit, a fraction of a second after the Big Bang, the young universe was a small energy bubble with slight density variations. These variations had significant implications. Through cosmic inflation, the observable universe expanded from marble size to trillions of kilometers in a fraction of a second. This rapid expansion stretched the density differences from subatomic to galactic scales, resulting in regions of varying density. After inflation ceased, gravity started pulling things back together. Denser regions eventually evolved into galaxy groups like our Local Group. This is our corner of the universe. However, beyond these denser regions, the universe's expansion has continued. This means that the Local Group is surrounded by other structures that are not gravitationally bound to it. As the universe expands, these structures move farther away from us. Complicating matters, the universe's expansion is accelerating, a phenomenon we attribute to dark energy. For now, it's sufficient to know that the universe's expansion is gaining speed. This acceleration creates a cosmological horizon around us. Anything beyond this horizon is moving away from us faster than light. Thus, it becomes permanently unreachable. In a way, it's similar to the event horizon of a black hole, but surrounds us. 94% of the galaxies we currently see have crossed this horizon and are forever lost to us. So how can we still see them if they're unreachable? Light takes time to travel, and we are seeing the light from these galaxies as they were when they were closer to us. Therefore, the observable universe is larger than the portion we can interact with. In essence, the universe is displaying unreachable galaxies to us. We can never know their current state, but their ancient light will continue to reach us for a long time. Eventually, all structures outside the Local Group will cross our cosmological horizon. Once that happens, their light will no longer reach us, and they will disappear from our view. However, about 6% of the observable universe is still within our reach, consisting of galaxy groups less than 18 billion light-years away. Although they are receding, they are doing so slowly enough to remain accessible, although the window of opportunity is closing. Even a Type 3 civilization would find it extremely challenging to reach these groups. For example, reaching the Maffei group, the closest galaxy group outside the Local Group, would take 11 million years at light speed. It's highly unlikely that humans will ever venture beyond the local group, given current technological limitations. The local group is probably the largest structure we will ever be a part of. Even interstellar travel within the local group would be a monumental achievement. Colonizing this region would already be a significant accomplishment, accounting for an infinitesimally small fraction of the observable universe. As dark energy continues to push the universe away from us, the local group will become increasingly gravitationally bound. Eventually, its galaxies will merge into a single large elliptical galaxy, tentatively named Milkdromeda, in a few billion years. This event may even trigger a brief resurgence in star formation. However, galaxies outside of Milkdromeda will eventually become too distant to observe. At that point, no information from outside the local group will ever reach us again. In the distant future, beings born in Milkdromeda may believe that their galaxy is the entire universe. They will see nothing but emptiness when they look into space. They won't be aware of the cosmic background radiation or the Big Bang. They may believe the universe is static and eternal. Milkdromeda will be an increasingly dark island in the universe. Nevertheless, the local group, with its trillion stars, provides a sufficiently large playground for humanity for the foreseeable future. We haven't yet figured out how to leave our solar system, and we have billions of years to explore our galaxy. We are fortunate to exist at a time when we can observe not just our future, but also our distant past. The universe, as far as we understand, has no boundaries and extends infinitely in every direction. Moreover, galaxies are uniformly distributed throughout this limitless expanse. This idea is derived from two key observations. Firstly, the observable universe appears to be both uniform and flat when viewed on a cosmic scale. Uniformity implies that clusters of galaxies are more or less evenly dispersed across large distances. Flatness indicates that, on a grand scale, the fabric of space-time is neither curved nor distorted. This suggests that the universe doesn't loop back on itself like a sphere would, which would imply a finite universe. The flat nature of the universe is actually a consequence of its uniformity. This is because localized concentrations of mass, such as moons, planets, stars, and galaxies, are what cause space-time to curve. However, these celestial bodies are minuscule in comparison to the universe as a whole, making their impact on the curvature of space-time negligible at cosmic scales. When you average out the mass distribution of all these objects, you find that it remains constant across the universe. The second key observation is that the region of the universe we inhabit is not unique or exceptional in any way. Given that the observable universe is flat and uniform, and considering that our local region is not special, it follows that the entire universe must also be flat and uniform. The only logical way for the universe to be consistently flat and uniform is for it to be infinite and lack any boundaries. While this idea is challenging for our limited human cognition to grasp, it's the most logical inference based on scientific data. If you were to travel in a spaceship in a straight trajectory indefinitely, you'd never encounter a wall, a limit, an edge, or even an area devoid of galaxy clusters. But how can an edgeless universe coexist with the concept of the Big Bang? If the universe began as something finite, shouldn't it remain finite? The answer is that the universe was never finite to begin with. The Big Bang wasn't akin to an explosion on a table that expands to fill a room. Rather, the Big Bang occurred simultaneously everywhere in the universe. This is why the cosmic microwave background radiation, a remnant of the Big Bang, is omnipresent in space. Even today, any part of the universe we observe shows this background radiation. The universe didn't expand as a physical object into existing space. Instead, space itself expanded. The universe began as something infinitely large, and has since grown into something even more infinitely large. While the concept of infinity is hard for humans to fully comprehend, it remains a valid and scientifically sound idea. In fact, it's entirely plausible in scientific terms for something that is already infinite to continue growing. It's important to note that humans can only perceive a portion of the entire universe, which we refer to as the observable universe. Because the speed of light is finite, it takes a specific amount of time for light to cover a given distance. There are regions in the universe that are so distant that their light hasn't had sufficient time to reach Earth since the universe's inception. Given that light travels at the maximum speed attainable, This implies that no form of information or signal from these remote areas has reached Earth yet. These regions are essentially beyond our current observational reach, or outside our observable universe. Every point in the universe has its own observational sphere, beyond which it cannot perceive. While our observable universe does have a boundary, it's not a physical wall or a massive void. This boundary simply delineates the regions that we can currently observe from those that are beyond our current observational capabilities. Even though the observable universe has a boundary, the entire universe is infinite and lacks any such edge. As time progresses, the light from increasingly distant points in space has the opportunity to reach Earth, causing our observable universe to continually expand. One might assume that given infinite time, the entirety of the universe would eventually become observable. However, there's a complicating factor. The universe itself is also expanding. While the current rate of expansion is not as dramatic as it was during the Big Bang, it remains a significant and ongoing process. Due to this cosmic expansion, galaxy clusters are consistently moving farther apart from each other. Some galaxies are at such a great distance from Earth that the universe's expansion causes them to move away from us at speeds exceeding that of light. Special relativity prohibits two local objects from exceeding the speed of light relative to each other. But it doesn't prevent two distant objects from moving apart faster than light due to the universe's expansion. Because these far-off galaxies are retreating from Earth faster than the speed of light, their light will never reach us, regardless of how long we wait. Consequently, these galaxies will perpetually remain outside our observable universe. In other words, while the size of our observable universe is growing, the actual universe is expanding at an even faster rate. The boundary of what we can observe can't keep pace with the universe's expansion, leaving many galaxies forever unobservable. Despite these observational constraints, the universe itself remains boundless. Approximately 13.75 billion years in the past, the universe was born. Almost immediately, the first rays of light began to traverse the cosmos, filling the nascent universe. At the same time, the universe itself was undergoing expansion. After an initial rapid inflation, the pace of this expansion slowed down. However, due to the effects of dark energy, the rate at which the universe is expanding has been progressively accelerating. In essence, the universe has been enlarging at a continuously faster pace since its creation. Experts in cosmology calculate that the most ancient photons we can detect have journeyed a span of between 45 and 47 billion light-years from the moment of the Big Bang. This implies that the diameter of the universe we can observe is around 93 billion light-years, with a small margin of error. This observable universe encompasses all the elements we can see, from quarks and quasars to stars, planets, nebulae, and black holes. However, it's important to note that the observable universe only includes the light that has had the opportunity to reach us. How can the observable universe have a diameter of 93 billion light-years when it's only around 13.8 billion years old? This apparent contradiction can be resolved by understanding a key aspect of physics, which also informs us about what might exist beyond the observable universe and whether we could ever reach it. According to the theory of special relativity, objects that are in close proximity cannot exceed the speed of light relative to each other. However, this rule doesn't apply to objects that are far apart, especially when the space between them is expanding. In essence, it's not that the objects themselves are exceeding the speed of light. Rather, the space between them is growing, making them recede from each other at incredible velocities. Ultimately, this suggests that to reach the edge of the observable universe, one would either need to achieve speeds greater than light, which most physicists consider unattainable, or bypass the limitations of space-time. This could perhaps be done through the use of wormholes or warp drives, though most physicists also view these as highly unlikely. According to the concept of cosmic inflation, the entire universe is estimated to be at least 10 to the power of 23 times larger than what we can currently observe. There's a vast amount of universe that remains beyond our perception. So what are we actually not seeing? What exists beyond the limits of the observable universe? Regrettably, since it's beyond our observational capabilities, we can't definitively say what exists in those uncharted regions. Nevertheless, there are multiple theories that attempt to explain what might be out there. The first theory, despite its oddness, is relatively straightforward to understand. Astronomers propose that the space beyond our observable universe could be an endless field of cosmic features similar to what we see within our observable limits. This idea seems reasonable, as it's unlikely that one part of the universe would differ significantly from what we can observe. After all, it's hard to imagine a universe that comes to a sudden stop, as if hitting a colossal barrier at its boundary. Therefore, the concept of an infinite universe is somewhat intuitive, but the term infinite implies that, beyond what we can observe, there exists not just more celestial bodies like stars and planets, but also every conceivable thing, literally every imaginable entity. If this theory of an infinite universe is accurate and we take it to its logical end, then somewhere in the cosmos, there exists another individual who is an exact replica of you in every conceivable way. Additionally, there would be versions of you with minor differences. Perhaps one is an inch shorter, another met an untimely end 5 years ago, or another is missing a finger. In fact, this alternate you might be watching this video at this very moment, the only distinction being they just engaged in nose-picking while you did not, or perhaps you did. The idea is mind-boggling, but then again, the concept of infinity is inherently difficult to grasp. Another hypothesis focuses on a phenomenon known as dark flow. In 2008, astronomers made a puzzling discovery. Clusters of galaxies were all moving in the same direction at an astonishing speed, exceeding 2 million miles per hour. One potential explanation for this could be enormous structures beyond the observable universe exerting a gravitational pull. As for the nature of these structures, they could be anything. Inconceivably large concentrations of matter and energy, or even strange distortions in space-time that channel gravitational forces from other universes. We simply have no idea what these colossal entities might be. It's worth noting that recent studies have attempted to disprove the dark flow theory, although this refutation is still a subject of debate. Another possibility considers a cosmos made up of multiple universes. Some theorists propose that our entire universe might be just one bubble among a vast collection of other bubbles, a concept known as the multiverse. Intriguingly, this theory suggests that these individual universes can interact with each other. Gravitational forces could potentially flow between these parallel universes, and when they collide, an event similar to the Big Bang that birthed our universe could take place. These theories represent just a handful of the more widely accepted speculations. Theoretical physics is an enthralling and occasionally whimsical field of study. While most individuals may not profess to have a deep understanding of this scientific domain, its complex principles often make their way into popular culture. Words like nuclear, quantum, and multiverse frequently play pivotal roles in our favorite television shows and movies. On the flip side, some of the more complicated theories in theoretical physics can sometimes resemble metaphysical or philosophical concepts more than they do traditional science. Some of these theories even seem to bridge the gap between scientific inquiry and religious or spiritual beliefs, eliciting either awe or skepticism, depending on who is listening. For example, consider the notion of extra dimensions. Many people might interpret this to mean parallel universes, where conditions are either slightly or significantly different, commonly referred to as the multiverse theory. However, the true scientific theory of extra dimensions is concerned with the possibility of dimensions that exist beyond the ones we can directly perceive. Though such conversations may seem speculative or even fantastical, they are essential for our understanding of how the universe operates. If we can determine the number and characteristics of the dimensions that make up our universe, we could potentially arrive at a theory of everything, which would offer a unified understanding of all the laws that govern the universe. To simplify, a dimension is any mathematical variable that can be measured. This typically refers to either a physical attribute, such as length, width, and depth, or a temporal attribute like time. In our everyday experiences, we encounter 3 spatial dimensions that define the geometry of all objects in terms of the x-axis, y-axis, and z-axis. However, to fully understand the laws of nature, scientists argue that a 4th dimension, which is time, must also be considered. Simply knowing an object's location in 3-dimensional space is not enough. Its temporal location is equally important. Beyond these 4 dimensions, theoretical physicists suggest that there may be additional dimensions in existence. The exact number of these dimensions is still a matter of debate, but the ultimate goal is to unify the various laws that govern the universe, a quest that has been ongoing for approximately a century. This endeavor is largely fueled by two seminal scientific theories, quantum mechanics and general relativity. Quantum mechanics emerged in the early 20th century and had several key figures, including Max Planck, Werner Heisenberg, and Erwin Schrödinger. General relativity, on the other hand, was initially proposed by Albert Einstein, although it was built upon earlier theories. It's worth mentioning that Albert Einstein also made significant contributions to quantum mechanics through his research on the behavior of light. Quantum mechanics is concerned with how energy and matter interact at the atomic and subatomic levels, while general relativity focuses on how matter, energy, and space-time behave at larger scales, especially in the presence of gravitational forces. Interestingly, despite nearly a century of research and development, scientists have yet to find a way to reconcile these two theories into a single, coherent system. Both quantum mechanics and general relativity work well on their own terms, but how they can be integrated into a unified theory remains a significant mystery. After many years of exploring the natural world and its underlying principles, scientists have concluded that four basic forces govern all interactions between matter and energy. These forces, along with the fundamental particles that make up all matter like quarks, leptons, gauge bosons, and scalar bosons, are components of the Standard Model in the field of particle physics. The four forces are electromagnetism, weak nuclear force, strong nuclear force, and gravitation. The first three forces are covered by the scientific area known as quantum mechanics and are linked to specific subatomic particles. Electromagnetism is connected to electrons, a type of lepton, which are the key players behind electricity, magnetism, and all kinds of electromagnetic radiation, including visible light, heat, microwaves, radio waves, ultraviolet radiation, and gamma rays. The weak nuclear force is involved in interactions between subatomic particles that lead to the radioactive decay of atoms. This force is connected to particles smaller than protons, known as bosons. At higher energy levels, this force combines with electromagnetism, resulting in the term electroweak force. The strong nuclear force is in charge of particles about the size of protons and neutrons, collectively referred to as hadrons. This force is named strong because it is approximately 137 times more powerful than electromagnetism, millions of times stronger than the weak nuclear force, and 10 to the power of 38 times stronger than gravitation. It brings quarks together to form larger particles like protons and neutrons and binds them to create atomic nuclei. Lastly, gravitation is the weakest among the four forces and governs interactions between massive objects like asteroids, planets, stars, galaxies, and the large-scale structure of the universe. Unlike the other three forces, there is no known subatomic particle that is associated with gravitation or gravitational interactions. This is why scientists often study physics in terms of either quantum mechanics or general relativity, depending on the scales involved, but generally not both at the same time. Because of this separation, scientists have been trying to develop a theoretical framework that unifies gravity with the other forces, generally falling under the categories of quantum gravity or a theory of everything. The quest for a unified field theory that combines gravitation and electromagnetism can be traced back to German physicist Theodor Kaluza. In the year 1921, he published a paper that extended Einstein's field equations to include a fifth dimension, adding to the conventional four dimensions of space and time. In the year 1926, Oskar Klein, a Swedish theoretical physicist, provided a quantum interpretation of Kaluza's fifth-dimensional theory. In Klein's version, the fifth dimension was compact and microscopic, taking the shape of a circle with a radius of 10 to the power of negative 30 centimeters. During the 1930s, work on the Kaluza field theory was further developed by Einstein and his colleagues at Princeton University. By the 1940s, this theory was formally completed and was given the name Kaluza-Klein theory. The theories of Kaluza and Klein laid the groundwork for the emergence of string theory, which was first proposed in the 1960s. By the 1990s, various adaptations had surfaced, including superstring theory, loop quantum gravity, M theory, and supergravity. Each of these theories suggests the existence of extra dimensions, hyperspace, or something similar. To summarize, string theory posits that the point-like particles of particle physics are actually one-dimensional strings. At distances greater than the string scale, these strings appear as ordinary particles, with their mass, charge, and other properties determined by the string's vibrational state. In one such state, the string corresponds to the graviton, the hypothetical particle responsible for gravitation. Superstring theory, a variant of string theory, requires the existence of 10 dimensions of spacetime. This includes the 4 dimensions we readily perceive, namely length, width, depth, and time, and an additional 6 that are not directly observable. These extra 6 dimensions are compactified into a minuscule space. At the string scale, which is 10 to the power of negative 33 centimeters, these dimensions are too small to be directly detected. According to this theory, the 5th and 6th dimensions deal with possible worlds that originated from the same initial conditions as ours. The 5th dimension includes worlds with slightly different outcomes, while the 6th dimension would display a plane of such possible worlds. The 7th dimension allows for the visualization of possible worlds that began with different initial conditions and then diverged infinitely, which is why the term infinity is often used to describe them. The 8th dimension would offer a plane of these infinities, while the 9th dimension would encompass all conceivable universes and physical laws. The 10th dimension would provide access to every conceivable outcome of cosmic evolution. Beyond this point, nothing can be observed by beings that exist within the space-time continuum. M-theory, a framework that unifies 5 separate superstring theories, proposes that there are 11 dimensions, 10 of space and 1 of time. This variation of superstring theory is appealing due to the phenomena it anticipates. For instance, M-theory predicts the existence of the graviton, aligning with string theory's overall explanation for quantum gravity. It also forecasts a process akin to black hole evaporation, where black holes emit Hawking radiation and gradually lose mass. Some versions of superstring theory even predict the existence of Einstein-Rosen bridges, commonly known as wormholes. Another approach, loop quantum gravity, suggests that gravity is fundamentally different from the other basic forces, and that spacetime itself consists of quantized, discrete units, shaped like tiny, one-dimensional loops. Some iterations of supergravity theory also advocate for an 11-dimensional model of spacetime, comprising 4 familiar dimensions and 7 dimensions in hyperspace. Additionally, there's brane theory, which posits that the universe consists of multidimensional vibrating membranes that possess mass and charge and can move through spacetime. As of now, there's no experimental proof for the existence of extra dimensions, hyperspace, or anything beyond the 4 dimensions we can perceive. This leads to a lingering question. If extra dimensions are essential for the laws of physics to be coherent, why haven't we been able to confirm their existence? 2 possibilities exist. First, our current understanding of physics could be incorrect, or second, the dimensions beyond the 4 we experience could be so subtle or minuscule that they elude our current experimental methods. The first possibility appears highly improbable, given that ongoing experiments, such as those conducted with the Large Hadron Collider, have validated the standard model of particle physics. Likewise, general relativity has been repeatedly confirmed since Einstein introduced it in the year 1915. This leaves the second possibility, that extra dimensions are too small or subtle to be detected with current techniques. One well-examined idea is that these dimensions are curled up at microscopic scales, making their properties measurable only at subatomic levels. Another concept is compactification, where certain dimensions are either finite or time-bound. In essence, this theory suggests that these curled-up dimensions become extremely small or loop back on themselves to form circles. If this is accurate, then the 6 additional dimensions would likely resemble a Calabi-Yau manifold, which satisfies the requirements for the 6 invisible spatial dimensions in string theory. For astrophysicists and theoretical physicists, the notion of compactification and minuscule extra dimensions explains why the universe has persisted for billions of years. If these dimensions were larger, they would accommodate enough matter to initiate gravitational collapses, leading to the formation of black holes that would consume the universe. the universe's continued existence after approximately 13.8 billion years, without showing signs of disintegration, lends credence to this theory. Alternatively, the laws of physics might operate differently in these extra dimensions. Either way, the question of how to observe and study them remains unanswered. So, if the universe does indeed contain imperceptible extra dimensions, how can we discover evidence for their existence and understand their characteristics? One avenue is through particle physics experiments, like those conducted by the European Organization for Nuclear Research, the entity that operates the Large Hadron Collider. At this facility, scientists accelerate particles to high energies, collide them, and then analyze the resulting array of subatomic particles. Detectors collect data on these particles, such as their speed, mass, and charge, to determine their identity. Theories involving extra dimensions predict the existence of heavier counterparts of standard particles that appear at increasingly higher energies as they traverse smaller dimensions. If such particles were discovered, it could indicate the presence of extra dimensions. Another approach is to look back in time to the cosmic dawn, roughly 100 to 500 million years post-Big Bang, when the first stars and galaxies emerged. Even if extra dimensions are undetectable today, they would have influenced the universe's evolution from its inception. Currently, astronomers lack the capability to peer this far back in time, but this will change soon due to next-generation telescopes like the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, the Extremely Large Telescope, and the Giant Magellan Telescope. This aligns well with ongoing dark matter and dark energy surveys that aim to measure their impact on cosmic evolution. Since some theorists suggest that extra dimensions could clarify the dark universe, these observations could solve multiple mysteries simultaneously. This dual approach mirrors our existing understanding of the universe, which is comprehensible only at the largest scales through general relativity and at the smallest scales through quantum mechanics. By observing the universe through both a wide and narrow lens, we might account for all the forces that govern it. Much like other candidates for a theory of everything, the idea that the universe comprises 10 or more dimensions is an attempt to reconcile all known physical laws. It's akin to assembling a puzzle where each piece is understood, but the overall picture remains elusive. Simply matching pieces where they seem to fit isn't sufficient. We also need an overarching framework, a conceptual image of the final outcome, to guide our efforts and anticipate how everything will eventually come together. For almost a century, scientists have struggled to merge the principles of quantum mechanics, which governs the tiniest particles, with the vastness described by Einstein's general relativity. Yet, a perplexing implication emerges. These theories seem to necessitate the existence of multiple universes, or a multiverse. Take, for instance, Schrödinger's quantum equation, which suggests a multiverse during wave collapse. Similarly, string theory, which proposes that the cosmos is composed of minute oscillating energy strings, also implies a multiverse. However, the existence of such a multiverse remains unproven, its nature elusive, and the potential for interaction uncertain, even if the mathematical evidence is compelling. This raises an intriguing thought. If multiple universes do exist, is it possible for us to explore them? Physicists haven't quite determined how we might interact with alternate universes. The approach largely hinges on the specific type of multiverse in question. In the many worlds interpretation, we constantly give birth to new realities or universes. Every decision we make or route we take leads to the creation of alternate realities where different choices are made. For instance, if you choose to pursue a romantic relationship, another version of you opts against it, leading to a separate timeline. Later on, if you decide to tie the knot with that person, another version of you chooses differently, spawning yet another reality. This concept traces back to Erwin Schrödinger's quantum wave function theory, which posits that a particle remains in a state of multiple possibilities, known as superposition, until observed. Upon observation, this superposition collapses, pinpointing the particle to a specific state. The mystery, however, is why this collapse occurs. Hugh Everett, an American physicist who introduced the many worlds interpretation in 1955, argued that the wave doesn't actually collapse. Instead, all potential outcomes manifest, but we're only conscious of the one we live through. The rest diverge into alternate timelines. Given that the entire universe is part of this overarching wave of potential outcomes, it continually bifurcates into new realities. Currently, while some physicists argue that if new timelines are being created, we'll remain oblivious to them, others hold on to the hope that advanced quantum computers might one day capture these divergences. There's also a belief that in the future, we might be able to integrate ourselves into these quantum systems, potentially offering insights into the lives of our alternate versions. Alternative multiverse theories propose the existence of universes within our own timeline, but they're simply too distant for us to observe. These ideas are supported by the mathematical frameworks of string theory and the eternal inflation theory. The latter theory posits an endlessly expanding multiverse that gives birth to new bubble universes. However, due to their immense distances, we're unlikely to ever come across them. These universes could be like sheets or brains drifting in the vastness of space, each characterized by its unique extra-dimensional properties. Alternatively, they could be endless potential bubbles birthed from the expansive stretch of the fabric of space and time, often referred to as quantum foam or space foam. Each of these bubbles has the potential to evolve into its own universe. Some hypotheses suggest that the distinct physical laws governing these universes might lead them to implode before they can form stars, or that they be inhospitable to human life. Conversely, others argue that given an infinite number of such universes, a few would inevitably share the same physical laws as ours, much like an infinite number of offspring from a couple would eventually result in at least two with identical genetic makeup. However, the idea of interacting with these universes poses a dilemma. It would be fascinating if they could softly touch each other. Envision a scenario where, while strolling down a lane, you suddenly find yourself facing a different universe where your usual grocery store stood. Yet, this scenario is deemed improbable by physicists, who believe that the collision between two such bubble universes would be catastrophic, potentially even sparking events like the Big Bang. Another method to traverse between universes could be through wormholes, essentially tunnels formed by linking two black holes where immense mass has warped space-time into a funnel-like shape. This would allow for rapid travel across vast spaces, akin to passing through a mountain tunnel instead of navigating over or around it. Einstein's general relativity suggests that a black hole might not culminate in the devastating gravitational force of a singularity, but could channel quantum data to a white hole on the opposite side. These hypothetical passages are termed Einstein-Rosen bridges. A white hole is often conceptualized as the reverse of a black hole, propelling matter outward, while wormholes draw them in. While white holes remain unobserved, the search continues. Some speculate the existence of a mirrored or alternate universe, operating in reverse time, linked to our own. Another proposition is that quantum entanglement might bridge the two extremities of a black hole, forming a wormhole. Beyond wormholes, there might be other means to reach alternate universes. Perhaps we'll uncover a dimension intersecting space-time, or future civilizations or advanced entities might develop faster than light travel, essential for covering the immense gaps between universes without wormholes. For now, it's intriguing to ponder the adventures of an alternate version of oneself in a distant realm. As scientists delve deeper into understanding the origins of the universe, tracing back to the Big Bang, they are also attempting to predict its eventual fate. The rapid acceleration of this expansion presents multiple scenarios. The universe might stretch itself to a point of rupture, resulting in a cataclysmic Big Rip. On the other hand, it might reverse its trajectory, contracting back to its primordial state in a big crunch. There's also the possibility of the universe gradually losing its heat and energy, leading to a cold, lifeless expanse known as the Big Freeze. With theoretical physicists suggesting that the universe might have a predetermined expiration date, possibly between 2.8 billion to 22 billion years from now, the urgency to understand its trajectory has never been more pressing. Some even posit that the final countdown towards its end might have already commenced. This leaves us with a profound question: what is the ultimate fate of our vast universe? Through the examination of ancient luminescence, researchers can observe the residual radiation from the Big Bang, commonly referred to as the cosmic microwave background. The special theory of relativity suggests that time is not absolute. The principle is that the quicker one travels, the more time seems to slow down from another's perspective. In a universe with galaxies that are expanding and stars and planets that are rotating, the perception of time is not consistent, making the past, present, and future subjective. Using this concept and information from studies on the cosmic background radiation, the estimated age of the universe has been determined to be approximately 13.799 billion years. This estimation provides insights into the potential end of the universe. Let's take a closer look at 3 hypotheses on how this result could arise. The primary hypothesis suggests the universe will conclude in a big rip, when the force of its expansion surpasses its inherent gravitational pull. This event would dismantle galaxies, subsequently affecting black holes, stars, and even Earth itself. The Earth, along with all of humanity, might gradually degrade into radiation, implode, or be torn asunder as the universe's expansion intensifies. This would result in a universe dominated by isolated, individual particles. Up until approximately 5 billion years ago, the universe expanded at a leisurely pace due to its dominant gravitational force. However, in more recent times, this expansion has quickened, with many pointing to dark energy as the cause. For the Big Rip scenario to play out, dark energy has to overpower gravity to an extent where it can disintegrate single atoms. A couple of years ago, Marcello Disconzi, a mathematics assistant professor at Vanderbilt University in Tennessee, alongside physics professors Thomas Kephart and Robert Scherer, formulated a fresh mathematical framework for the Big Rip. According to this model, the universe's expansion rate will ultimately reach infinity. While past models often overlooked viscosity, Disconzi's theory emphasizes that it's the universe's viscosity that triggers its catastrophic end. His concept draws inspiration from ideas presented by French mathematician André Lichnerowicz in the 1950s. Another hypothesis regarding the universe's eventual fate is termed the Big Crunch. Should the universe's matter not expand indefinitely and instead begin to diminish over time, gravitational forces could take precedence. This would lead the universe to contract, resulting in the collision of stars, planets, and entire galaxies. Essentially, the universe would implode upon itself. In simpler terms, if the universe's expansion decelerates and the events of the Big Bang unfold in reverse, all would collapse back into a single point. Scientists from Denmark have recently asserted that this phenomenon, termed a phase transition, might already be underway in our universe, essentially eroding the cosmos. A phase transition can be likened to the process when water becomes vapor. As per the Higgs theory, such a transition took place a mere 1/10 of a billionth of a second post the Big Bang, leading to a change in the structure of space-time. During this shift, what was once a void became permeated with an unseen entity now termed the Higgs field. If a concentrated Higgs field is present, the scientists from the University of Southern Denmark posit that a bubble of this condition could manifest anywhere in the universe at any moment. Their calculations indicate that this bubble might then proliferate at light speed, occupying all of space and transitioning the current Higgs field into a different state. Quantum mechanics principles also hint that random particles can spontaneously emerge from a void, a phenomenon frequently observed in particle physics tests. Some theorize that dark energy might trigger such quantum fluctuations, potentially leading to a new Big Bang that concludes our current timeline and initiates a fresh one. Based on our present understanding of physics, this is considered the least probable of the proposed outcomes, yet it remains a topic of discussion. The third proposition suggests that the universe might conclude with a big freeze, ironically also termed heat death. This outcome is deemed the most probable based on our current understanding of physics and the universe. Dive deeper. What does Einstein's theory of relativity entail? This concept is rooted in the idea that, within the universe and other closed systems, entropy will continue to rise until it attains its peak value. Entropy stems from thermodynamic principles concerning energy, specifically highlighting the transition of everything in the universe from a state of order to one of chaos. Hence, entropy gauges this transformation. When entropy hits its zenith, it's theorized by physicists that heat within the system will equalize. This implies there would be no potential for usable energy or heat, leading the universe towards a heat death. In essence, all mechanical activity in the universe would halt. Amidst this big freeze, the universe is hypothesized to expand to such an extent that gas reserves become exceedingly dispersed, preventing the birth of new stars. In this scenario, time transforms into an infinite expanse, where events cease to occur due to the near absence of energy in the universe. Thanks to Brilliant for sponsoring this video. Brilliant offers specialized courses that can help you unravel such big scientific questions. If you're keen on problem solving, logical reasoning, critical thinking, and more, Brilliant is the destination for you. Brilliant courses are crafted to teach you how to think and solve problems through interactive lessons. It's designed for everyone. For curious learners of all ages, both professional and inexperienced, and anyone wanting to learn or enhance their skills in math, science, technology, and engineering. I truly appreciate and admire the way Brilliant's lessons focus on scientific thinking. Their comprehensive and interactive approach provides a deeper insight, enabling me to grasp and understand scientific principles more effectively than ever before. In the scientific thinking course, you'll have the opportunity to harness the power of scientific principles. By doing so, you can tackle intriguing puzzles and make informed predictions about the world around you, shedding light on everyday phenomena. Curious about a topic and want to learn more? Check out the link brilliant.org/bigscientificquestions in the description below and start exploring with Brilliant. Enjoy a 30-day free trial, and if you're among the first 200, get 20% off Brilliant's annual premium subscription.